Hello everyone, I'm Zheng from Zhejiang University. Today I will introduce our work, NVAlloc, Rethinking Heap Metadata Management in Persistent Memory Allocators. Persistent memory, or PMEM, is a high-performance bit-addressable memory device that resides on the memory bus. It has nearly the same speed and latency of DRAM, and the non-volatility of flash device. The persistent memory allocator is the fundamental building block for developing high-performance applications on PMEM. It is the middleware between user application and operating system. It provides recoverable and fine-grained user-level persistent memory management. For persistent memory allocator, memory leak is one of the problems that must be solved. Memory leaks are more problematic for persistent memory than volatile memory because the leaks are persistent. Besides, persistent memory faces a new class of memory leaks resulting from power failures. Consider a linked list whose nodes are allocated by a persistent memory allocator. Now we want to add a new node to the list. We will first allocate a new node, do some initialization work on it, and finally we will add a pointer to the previous node to link it in. Now if a crash occurs after the new node was allocated, but before it was linked to the previous node, the persistent allocator will remember the allocation, while the data structure will not, leading to a persistent memory leak. Previous works use different consistency models to address persistent memory leaks. The first model is Rethinking-Heap-Metadata-based model, which is used by NVAlloc and Allocator. They add a Rethinking-Heap to record changes to Allocators' metadata, and memory leaks can be eliminated through undoing the changes. The second model is post-crash garbage collection-based model, which is used by Makalu and NVAlloc. They use conservative garbage collection to rebuild allocators' metadata after the crash by traversing user data. This model can avoid the overhead of writing logs and flashing metadata, but it may limit certain functionality of type unsafe language like C++. The third model is the internal collection-based model, which is used by PMDK. This model gives the user an interface to traverse the memory blocks in the allocator. The user can detect memory leaks by comparing the allocator with their own memory blocks. Existing persistent memory allocators inherit mature designs from volatile memory allocators. For example, they usually divide memory allocation requests into large allocations and small allocations. For large allocations, allocators such as Makalu use chunks to manage memory regions. They put the metadata of these regions in the header of the chunk. Chunks are directly acquired from the operating system through file mapping. For small allocations, allocators such as PMDK use slabs to manage small memory regions. A slab is subdivided to memory regions of fixed size, and it uses bitmap to manage them. Slabs are acquired from large allocations. Existing persistent memory allocators also use thread local cache, or T-cache, to reduce lock contention in small allocations. Memory regions that are recently freed by a thread will be cached in its T-cache for future use. However, the mature designs from volatile memory allocators are not necessarily optimal for PMEM. This is because the real PMEM hardware, for example Intel Optane DC PMEM, has its own performance characteristics. It has better sequential access performance than random, and if a cache line is flushed repeatedly, the flush latency will be 8 times higher. Existing allocators are not aware of these PMEM characteristics. As a result, these induce performance issues such as frequent cache line reflush, and small random access. They also has memory fragmentation issues caused by static slab segregation. To address above issues, we present NVAlloc with 3 novel optimizations. Next, I will expand on these 3 topics. The first issue is cache line reflush, which frequently happens in small allocations. We run 4 well-known benchmarks to study the number of allocator-induced reflush. We observe that cache line reflushes account for up to 99.7% of flush operations. This is because allocators have a lot of small metadata objects, for example bitmaps in the slab header or log entries in the read-ahead log. They are smaller than 1 cache line size. For slab headers, when the bitmap is updated repeatedly, the same cache line should be flushed for persistence. For read-ahead log, when a new log entry is appended to the log, it may cause repeated flushes of the cache line at the tail of the log. To address this issue, we propose the first optimization named Interleaved mapping. The key insight is that the metadata of consecutive objects do not need to be consecutive, so we can assign repeated flushes induced by metadata modification to the different cache lines using interleaved mapping. For slab headers, we change the sequential mapping of bitmap to interleaved mapping. We distribute the bits describing the schedule of memory objects to different cache lines. We also use interleaved tcache layout to eliminate the impact of tcache on reflush issue. Please check the paper to find that. For read-ahead logs, we change the tail appending method in log structure to an interleaved appending method. New log entries are appended to different cache lines at the tail in turn. In this way, the allocator-induced cache line reflushes are eliminated. The second issue is small random access, which frequently happens in large allocations. To study the allocator access pattern to PMEM, we profile the memory addresses of flush operations when running the DBMS test. We observe that for managing the bookkeeping metadata, allocators issue a large number of small random reads to persistent memory, and the requested addresses are distributed in the whole heap space. The reason is that, to serve a large request, allocators typically use allocation algorithms, for example, best fit and first fit, to find a memory region of the most suitable size. After that, they in place update the bookkeeping metadata in the chunks header. The best candidate can be located in any chunk in the heap space, leading to small random accesses for updating its bookkeeping metadata. To eliminate the random access, we propose the second optimization, named log-structured bookkeeping. We decouple large allocation metadata into volatile indexes and persistent log-structured bookkeeping. For volatile indexes, NVAlloc uses the similarly extent-based approach as NVAlloc to manage large memory regions. Every large memory region is managed by a visual extent header, or VEH. A VEH is moved between the activated list, the reclaimed list, and the returned list to indicate the status of the corresponding extent. VEHs will be rebuilt after rebooting. In persistent memory, we use a persistent bookkeeping log to store the update to VEHs in a sequential pattern. The overhead of logging in allocators is very low. This is because we only store small essential metadata, and the size of log entries is unified, leading to a simplified log management process. In addition, we also use the interleaved appending method in bookkeeping log to avoid cache line reflush. The third issue is persistent memory fragmentation in small allocations. The fragmentation issue is intensified in PMEM because fragmentation cannot be eliminated by restarting the system. We run a popular fragmentation benchmark to study the memory usage of existing allocators. We find existing allocators require memory usage of up to 2.8 gigabit to manage the 1 gigabit live heap data. This is because the slab in allocators can only serve the requests of a fixed size. Mismatched slabs cannot serve the request even though they are mostly empty. Therefore, a new slab will be created to serve the request, and the free space in existing slabs will remain as fragmentation if the allocation pattern is changed after that. We use slab muffling to address the fragmentation issue caused by static slab segregation. The idea is that when memory usage of a slab is low, NVAlloc allows it to be transformed to a slab of another size class. During the transformation, the slab may store two types of data blocks of different sizes. The transformation is complete when all blocks of the previous size have been freed. We need to address two challenges in slab muffling. The first is the muffling scheme needs to guarantee the correctness of indexing of two types of blocks in one slab. The second is we need to minimize the overhead of managing these blocks. We use an example to show how slab muffling is performed. For a slab to be muffed, we first transform its bitmap. If the new block is occupied by old block or old blocks, the corresponding bit in bitmap will be set. And then, to manage the old blocks, NVAlloc adds new metadata in the slab header. The most important ones are count block and index table. Count block indicates the number of old blocks occupying a new block. The index table records the state of each old block for recovery. When an old block is released, the index table and the count block will be updated accordingly. The release of old blocks have a low cost because they are small in number. For the allocation and release of new blocks, they have no extra overhead because only the bitmap is used in the process, just like the operations in normal slab. For evolution, we use a Linux server with 64 gigabit DRAM and 256 gigabit PMEM. We use various workloads to show how NVAlloc outperforms other allocators in small allocation, large allocation, and memory usage. We compare NVAlloc with existing allocators in all consistency models. For small allocation, NVAlloc outperforms existing allocators by up to 60.4 times and 3 times in average. For large allocation, NVAlloc outperforms existing allocators by up to 57 times and 5 times in average. To further analyze these results, we use the Linux Perf tools to measure the breakdown of execution time of thread test and DVMS test. We notice that the performance improvement is mainly due to the reduction of the flash time. For small allocation, this is mainly because the cache line reflushes are eliminated. For large allocation, this is mainly because the small random flushes to PMEM are eliminated. We also evaluate the memory usage using Fragbench. NVAlloc reduces memory usage by up to 57.8% with performance overhead less than 5%. This is because NVAlloc allows slabs with low space utilization to be reutilized. Then this is a brief summary. We proposed a persistent memory allocator named NVAlloc to address performance and memory usage issues in existing allocators using interleaved mapping, log-structured bookkeeping, and slab muffling. NVAlloc significantly speeds up small and large allocations and reduces memory usage. The source code for NVAlloc is available on GitHub. Thank you very much.